Point groups. A point group is described by a characteristic assembly of symmetry operations. A certain number of symmetry operations with defined geometrical relations among themselves can be found for any given object. The object is said to have symmetry described by the given point group. Different groups which have different symmetry will be described with the different point groups. All symmetry elements present refer to a common point, the origo. The point group must fulfill the mathematical requirements. First one is the product of two operations is another operation in the group. And the second one is the identity element I is present. The third one is there is an existence of an inverse operator, that is R into R inverse, which is equal to I. We get the identity element. And the fourth one is associative multiplication of operators. Then in a general way we can say that collection of symmetry elements is called point groups. The symmetry elements are rotation, reflection, inversion, etc. There are 32 crystallographic point groups which consist of combinations of symmetry elements. The next is space groups. The combinations of 32 crystallographic point groups and the 14 Bravais lattices are give rise to 230 different space groups. The given crystal structure and a given structure type will be described within a given space group. That is, the Bravais lattice is defined together with the point of symmetry of the 230 space groups. 73 arises from combinations of Bravais lattices and the crystallographic point groups without any extra symmetry operations such as screw axis and glide planes being involved. The next topic is liquid crystals. Figure shows some of the liquid crystal type. What is the history of liquid crystals? In 1888, Reinitzer observed that as he heated cholesterol benzoate, the solid melt at 145 degrees Celsius into a liquid of a white turbid milky appearance. When this liquid is heated further, it undergoes another transition at 179 degrees Celsius, this time into a certain clear transparent liquid. The substance was further investigated by Lehmann, who found that the liquid actually exhibits optical anisotropy, that is birefringence property. The usual fact that the substance has the mechanical properties of a liquid, that is ability to flow and low viscosity, and the anisotropic optical properties of the crystal are prompted Lehmann to coin the descriptive name liquid crystals, which has been retained ever since. The liquid crystalline phase is often called the mesophase, and a substance having such a character a mesogon. Generally, there are two ordered phases of matter, that is translational order and oriental order, sometimes called orientational order. The characteristic property of translational order and oriental order are: translational order refers to the extent to which molecules or groups of molecules on average shows translational symmetry, but orientational order refers to the extent to which the molecules align along a specific direction on a long range basis. In a crystalline solid, molecules are ordered in both the above ways, that is, they are constrained to occupy specific sites in a lattice and to point their molecular axis in specific directions. On the other hand, molecules in a crystal diffuses randomly throughout the sample without any orientational order. Thus, a crystal has orientational and three-dimensional positional or translational order, whereas a liquid has none. Depending on the degree of translational order, liquid crystals are classified as, the main classifications are nematic, cholesteric, smetic. If there is no translational order, they are called nematic phase. The next is one-dimensional translational order, giving rise to smetic phases, and two-dimensional translational order giving rise to columnar or cholesteric phase. The general classifications are thermotropics and lyotropes. Smetic, nematic and cholesteric liquid crystals are included in the family thermotropics. Thermotropics are small organic molecules, usually rod-like or disc-like, which show mesomorphic behavior as a function of temperature. Lyotropic means these contains mixture of organic molecules. Quasicrystals. Quasicrystal, also called quasi-periodic crystal, formed atomically in a manner somewhere between the amorphous solids of glasses and the precise pattern of crystals. Like crystals, quasicrystals contain an ordered structure, but the patterns are subtle and do not recur at precisely regular intervals. Rather, quasicrystals appear to be formed from two different structures assembled in a non-repeating array. The three-dimensional equivalent of a tile floor made from two shapes of tile and having an orientational order but no repetition. Although when first discovered such structures surprised the scientific community, it now appears that quasicrystals rank among the most common structure in alloys of aluminium with such metals as iron, cobalt or nickel. While no major commercial applications yet exploit properties of the quasicrystalline state directly, quasicrystals form in compounds noted for their high strength and light weight, suggesting potential applications in aerospace and other industries.
Here I'm going to make some liquid crystals, and what I'm going to use is I'm going to use some cholesterol oleoyl carbonate mixed with some cholesterol pelargonite. And all you have to do to kind of make this into an experiment is try doing different amounts of each. So here we've got about 0.1 grams. There we go, 0.1 grams. All right, we're going to mix that with 0.2 grams of the carbonate version. We're going to get that in the same test tube, and then we're going to melt the two together. So when we melt the two together, there's going to be a chemical reaction between them. We're going to take that. It's going to be our liquid crystal, so we're going to get this in here, warm it up. So once that's completely melted together, we're going to take that, that's going to be our liquid crystal, and we're going to put it on top of this paper here. We're going to use that to kind of be able to run temperature tests on it, see how it turns out. But what you want to do when you vary this is you want to just vary how much of the two chemicals you use. There's also other chemicals you can add to this mixture to make different kinds. But you want to look then at when you'll get the liquid crystal state, what temperature range, and then also one of the fun things to do that we're going to do is look at what colors they'll change when you get them into the liquid crystal state. So now we'll go ahead and take this melted mixture and we're going to put it onto our context paper. And there we go. There's our liquid crystal. Probably go ahead and heat that up and we'll get our color scheme back. You can see a kind of ring of color right there. It's like a bluish silver with a little hint of rainbow. And so the temperature range for this is going to be similar to what the temperature of your hands are. You can actually pick it up, use the warmth of your hands to get it to change. So right in there you can see the liquid crystal hardening up. You can see some of that light properties there, the nice little rainbow. So here you can see some liquid crystals cooling down and you get that nice rainbow effect as they do. And here's ours. Very nice. So depending on how much you mix of each will influence what kind of patterns you get, and at different temperatures when they'll be.